So our last section is thermodynamics. We're going to talk primarily about gases, but we'll talk a little bit about energy involved in temperature changes. So before, when we talked about energy and we said friction would make something warm up, of course the friction makes it hotter, we'll talk about the equations that describe that. Okay? But first, this first chapter is kind of a little bit of a hodgepodge chapter. It has a bunch of little different concepts to introduce us to before we get to the next chapter. So we talk in this chapter about the periodic table. I didn't bring a periodic table with me, but I'm sure you've all seen one before. I can't remember exactly what it looks like. Yes, there is one in the book. Feel free to look that up. The periodic table has all of the different elements that we know of. I imagine we've all at some point in our life seen the periodic table, but it may have been a little while. There's two important numbers that you need to understand on the periodic table. I'll look at the one in your book here. There's a number up in the left-hand corner. That's the atomic number. Hydrogen is atomic number 1. Helium is atomic number 2. And so forth. We're not going to venture beyond really more than hydrogen, helium, and say oxygen or nitrogen, things that I'm hoping are fairly easy for you to find on the periodic table. The other number that's on here, underneath, is the atomic mass. So the atomic number is the number of protons that that particular atom possesses in its nucleus. The number of protons, and if it's a neutral atom, it will have the same number of electrons as well. It does not necessarily have the same number of neutrons. We have isotopes depending upon the number of neutrons it has, but we're not going to worry about isotopes in this class, so don't worry about that. The atomic mass is related to basically how much mass makes up your atom. So hydrogen, for example, 1. There's two ways we can write this. We can write this as 1U, where U is the atomic mass number, or unit. For those of you who had chemistry, you may have seen it as AMU. Same thing. I guess physicists are just lazier, so we just call it U. I don't know why. The other way we can write this is as 1 gram per mole. So it means the same thing. Now you have a conversion in the front of the book that converts U to kilograms. 1U, if someone doesn't want to look it up, it's like 1.66 something. Thank you. So 1U is 1.66 times 10 to the negative 27 kilograms. So helium, for example, 4 is 4U. We would multiply this number by 4 to find out how many kilograms one helium atom happens to possess. Okay. When we talk about gases, we tend to talk about pressure again, just like we did when we did our fluid chapter. We talk about volume, how much space it fills up, and its temperature. When we talk about how much gas we have, we tend to use the quantity of moles. We use a lowercase n to represent it. Moles is just a grouping of atoms or molecules. It's like saying I'm going to bake a dozen cookies. A dozen cookies just means I'm going to make 12 cookies. Moles is just a certain number of molecules. Avogadro's number tells us that there's 6.022 times 10 to the 23rd molecules per mole. So if you have 1 mole of gas, you have 6.022 times 10 to the 23 molecules. Now, whether those molecules are individual atoms or atoms bound together depends upon the type of gas it is. We're going to talk about 2 types of gases. There's certainly more than this, but we're going to focus on just 2. Monatomic gases. Mono meaning 1, atomic. Monatomic means they are individual atoms moving around. The atoms themselves do not bind together to form a molecule. So technically, 1 molecule for a monatomic gas is the same thing as 1 atom. Helium and anything below it in this column are all monatomic gases. They're called the noble gases. So helium, for example, if you have helium gas, all of the individual helium atoms are moving around individually. They'll run into each other maybe, but they don't bind together. Diatomic gases mean that 2 atoms bind together and they move as a combined particle. So 2 atoms bind together, create 1 molecule. So 1 molecule is made up of 2 atoms. The common ones that we'll use, oxygen. If you've ever seen oxygen gas written in symbol form, it's just O2, meaning there's 2 oxygen atoms. Nitrogen and helium, those are all diatomic gases.
Right. I think you said helium. Yeah. She wrote hydrogen.
Sorry, I may have said helium. I meant hydrogen. Thank you. Apologize. So hydrogen, nitrogen, and oxygen are the main diatomic gases we'll talk about. Or our problems will just tell us we have a diatomic gas and it doesn't really matter which gas it is. Just the fact that it's diatomic is all we need to know. Okay. So some terminology here. To represent symbolically the number of moles of gas we have, we're going to use a lowercase n. It has to be lowercase n. Because we're going to use a capital N to represent the number of molecules we have. So n is used for both, but uppercase versus lowercase is going to be the big difference. So number of molecules we have is capital N. Number of moles we have is lowercase n. And of course, Avogadro's number is also n, but a subscript of a. So these 3 are related. Avogadro's number represents a certain number of molecules per mole. So the number of molecules, the ratio of number of molecules over number of moles is Avogadro's number. Or we can say number of moles is equal to number of molecules over Avogadro's number. So we can easily convert between number of molecules and number of moles in any given problem. Why you would want one versus the other is just dependent upon what material information you're given in a problem or what you're being asked for. You may be told the number of moles, you may be told the number of molecules, and you may need the other. One other piece of information you'll need to be able to pull off a periodic table. For example, let's say we're solving a problem where we have 12 grams of water. When we deal with gases, we're not going to be dealing with mass. We'll be dealing with molecules or moles. So we need to be able to figure out how many moles 12 grams of water would be. Okay. Now hydrogen. On the periodic table, hydrogen is 1, and that means 1 gram per mole. Oxygen, if you look on the table, oxygen is 16. So that means it's 16 grams per mole. So what is water? 18 grams per mole. So if I have 12 grams of water, I can use this information that I know that there's 18 grams per mole to figure out the number of moles. To get the units to cancel, to get the grams to cancel, I need to write this as 18 grams on the bottom to 1 mole on the top. So 12 over 18, let's see, 12 is 2/3. So if we have 12 grams of water, that's the same thing as 2/3 of a mole. Which, knowing the number of moles, if we multiply it by Avogadro's number, that will tell us how many molecules we have. So pretty easy going back and forth. And for those of you who have had chemistry, you probably all handed this, and I'm sorry for boring you. Questions? So the only main things you're going to have to pick off the periodic table, say hydrogen, helium, oxygen, maybe some nitrogen. Be able to figure out the atomic mass, figure out the number of moles you have if you were given the number of grams.